Now we have a session. In fact, there will be this session and one more tomorrow of people who are not here. And I ask, so essentially this was kind of my first slide in my how I set the scene of this conference. And I want answer not just from people here. I don't want answer from people here, but also from people who are invited, but they couldn't come. So this is the email which I sent to to people who are invited before. I talked to them that I wanted that they come, and they cannot. And some of them sent something. So some of them sent some small video, and some of them sent some paragraphs. And so we'll try to present it here. So. And I think I would like to hear reaction on some of it. It's not just, so they will not react. It's not Zoom. This is just, yeah. Okay. So the first one is John Barrett, and he just sent a video. So this is simple.
Hello. Lev asked the question, why is the many worlds interpretation not the consensus? I think there are a couple of related reasons. One reason is that there are several quite different many world interpretations that we have available, and I think each of these comes with incommensurate virtues. The fact that we have a range of options available is illustrated by the fact that few of the current proposals look much like Everett's own account. Everett started with pure wave mechanics, and I think that's a great place to start. Pure wave mechanics is the standard formulation of quantum mechanics, but with no collapse of the quantum mechanical state. The question then is what we should add on top of that as auxiliary assumptions. For his part, Everett added a distinction between absolute states and relative states, and he added a typicality measure over branches. Everett's account had no synchronic or forward-looking probabilities, no probabilities at all. Specifically, branch weights were measures of typicality, not measures of credence or chance. Everett sought to show that the sequence of records for a relative observer in a typical branch will exhibit the standard quantum statistics. Now, for our part, we presumably want probabilities. And I would like to have standard forward-looking probabilities if those can be recaptured. But this is part of the problem. It's tricky to say how to get from pure wave mechanics to determinate records with standard forward-looking probabilities. And this is connected to the other reason for the lack of consensus. There's an uncomfortable trade-off, I think, between the elegance and the clarity exhibited in alternative readings of Everett. Let me give a quick example. I take it to be a subtle business, explaining how one gets fully determinate physical records and standard forward-looking quantum probabilities in the context of a decoherence formulation of quantum mechanics. It's also tricky to assess how well one has accomplished that at the end of the day. In contrast, it's perfectly clear, at least it's perfectly clear to me, how one gets determinate measurement records, determinate measurement outcomes, and standard forward-looking quantum probabilities on something like Albert and Lower's many minds formulation of quantum mechanics. But the conceptual cost in accepting a reading of Everett like that is prohibitive. And so this is the trade-off between elegance and straightforward approaches that are perfectly clear, but just aren't as compelling. I don't think we should have a consensus on a particular many worlds interpretation of quantum mechanics. Rather, I think the consensus should be that pure wave mechanics is the right place to start. and then we explore the possibilities and continue to explore them. All best wishes.
For me, it's really important. He expressed one opinion. He wants these forward-looking probabilities, and in this, when I gave us the first talk, this was set up. I think there are no forward probabilities in many words. That this is one of the features, which. So he says it's bad, and I think maybe it's unfortunate, but I think we can live with it. And I understand maybe some people think that Simon, or maybe I don't know, maybe David too, that one can put forward probabilities many words, which I think one cannot. And so I would like to hear some comments about this question now. Maybe Simon, because
I think that there's a very good reason why there's no consensus on many worlds if people take many worlds to involve the commitment to the view that there are no forward probabilities. I think for the majority of physicists that just rules it out of contention because quantum mechanics is about probabilities. So there you have it.
okay.
I think in this area we have to be careful to avoid getting bogged down in terminology. So there's the idea that, I know Henry Greaves thinks what David and I think, but says let's not call them probabilities, let's call them caring measures. And it's not a substantial issue. And then there's the issue about whether we have uncertainty. And I've been inclined to say we don't have uncertainty, but Paul now is saying, well, if you give non-degenerate probabilities, non-degenerate measures to different future outcomes, that's uncertainty. Who needs that? The uncertainty requires there's something about the future you are ignorant about. You just need to spread your credences over different outcomes. And this morning I was thinking that Tim says, oh, the crucial issue is, do you have alternative futures? And I'm inclined to say, I have alternative futures. It's just that my alternatives aren't fighting in the competition to become real. They're all going to become real, but they're all alternatives. So I think, have we got probabilities or not? That can't be the substantial issue. There must be some other way of framing the substantial issue. Maybe the substantial issue is to do with how are we going to act. Are we going to act in the sensible way?
I think, surely, I have caring measure, I have measure of existence. I do not have uncertainty. I know exactly what will happen from now on in my branch. Yeah. And so I cannot ask it. I believe, maybe it's too simple, again, semantics. For me, probability, you need a matter of fact for a fact. If A will happen and A may not happen, then I can ask what's the probability of A. But if A happened, definitely, this is, or maybe there is a different meaning. Oh, there are so many, there are typicality, credence, whatever. I don't understand image, typicality. I don't think one needed. But probability is for the case when you have a matter of fact which might not happen. Then you can ask, what is the probability? You can call typicality some other thing. I don't care. I don't think I need all the other names. But I think as uncertainty is important, there is no uncertainty.
In a sense, this is going to be a variant of David's point. I mean, let's stipulate that we understand Weidmann probabilities, we understand self-locating post-measurement probabilities. We're then going to need a decision process for handling forward-looking situations, whether epistemically in deciding what our strategy is of doing experiments, or pragmatically in deciding how to bet, or a mixture of both. And we're probably going to need to reason our way towards finding that what that strategy is it involves treating the mod-squared amplitudes of the branches as playing a functional role extremely close in form to probability. You know, I'm going to end up saying, for instance, if I say to you, I'll give you $1 billion if some radioisotope decays in the next 10 seconds, you choose the radioisotope. Of course, you're going to choose a radioisotope with a short half-life. And if I start quantifying that with odds, you're going to start using the number in that. And then at that point, once we have a probability surrogate in this case, it kind of starts to seem like a philosophy of language question, whether it's really probability or whether it's not, but it's not going to matter very much to the physics. And you can imagine if we decided, you can imagine like 100 years from now, 100 years from now, the textbooks will be saying, back in the early 21st century, people used the word probability differently, and the great Lev Weidman pointed out that actually this wasn't these were not true probabilities at all. In the 23rd century, having absorbed these insights, we now use the word probability in a different way from the people in the early 21st century. It wouldn't really matter very much. It wouldn't be that significant to whether we decided the theory is right or not.
What I believe is the message that if people believe in many words, they should change. The language is really a problem, and that they should specify. Now, my post-measurement probability is kind of only kind of an exercise to one, you have to accept the behavior principle. And my behavior principle is not because of this. This maybe strengthens the ideas. My behavior principle because I will have some descendants. And it's clear that if all descendants are identical, if they all have equal measure of equal measures, then I should care equally about them. But they are not. I don't believe that you can divide few branches, so they all have, in real life, the future branches are not equal. Some of them have small measure and some of them big measure. And then I can use this, I think, very natural idea that if the one can be split for more, such that they all will be equal, I will care about this thick one as if there are many of them, such that they're all equal. But again, this is for measure. I put my bets in all kind of similar betting experiment because I think about the future measure. I will be in all of them. There is no probability because there is no matter of fact. So I think I think this is exactly semantics. I think we have to develop and make it clear. There is no probability in the sense that one and not the other. There is a carrying measure because we'll have many and they're different.
Well, put it this way. I mean, look, suppose I'm planning Everett at 70 conference. I know. Let's say in Oxford, there's no plan for this. This is just an example. Everett at 70 conference in Oxford in 2027, and it's so important that I want to start planning years in advance. So, what time of year am I going to have this conference? Well, I'm going to think. Well, I'm not going to have it in March because in March the weather's probably going to be bad, and I'm going to have it in July because in July in the UK the weather's not probably good, but quite likely to be good. Now, maybe you should have it somewhere sunnier like Tel Aviv. But anyway, now the weather's chaotic. I mean, we could debate this as a physics point, but just let's stipulate the weather's chaotic. There's quantum branching. So I could say, well, no. What I strictly speaking mean is, I can imagine you're on the committee for this, and you challenge me and you say, no, David, don't say probably the weather will be nice. Just say something like you should be saying instead that there will be a larger fraction of branches by Caring measure in which the weather is nice, so hold the conference in July rather than March. And I think I'm going to say back to you, Lev, yeah, okay, fine. When I say probability, just read me as saying that. Your way of saying things is kind of cumbersome. I don't want to change my usage. We all know what I mean. And you just read me as meaning something different by probability.
Okay, I completely accept your idea. Shut up and use the many word interpretation.
I may have just said, I agree with what the two Davids have said, except that if you're trying to sell the Everett interpretation or many worlds interpretation to a broader audience, mostly people aren't going to spend a lot of time thinking about it before, should I read further? And if what they hear is there's no such thing as probability, I think a great majority just won't even pursue the many worlds interpretation further. They won't read the first 3 or 4 pages even, because what they've just been told just goes against everything that they think quantum mechanics is all about. So you can do tremendous damage to many worlds interpretation, I think, through selling it, trying to sell it as the framework in which there's no such thing as probability.
I don't think the lying will help. This will continue. If something is wrong, and it will not win in the future. But if there are more people and more people to want to make some comments, please.
Yeah, this is a short one. It is possible that we just live in a branch of worlds where it is not a consensus, right? That's all.
More comments? So we can have. Because I don't believe I can read it nicely. You can read it from here, or maybe from here.
Okay, I've never. Okay, I'm torn between two situations. One in which I had to repeat or give a talk based on what Stephen Hawking had written, which was believing that information was lost when I didn't believe that. And then my short reading yesterday in Jerusalem was something I did believe in. Okay, let's see. I don't know what this. Okay, I'm sorry. I haven't learned French, and I'm not sure how to pronounce this. Jean Bricmont. Anyway, whatever. Okay, the first objection concerns the Born rule. Suppose that the probability of having the cat alive or dead as a result of an experiment are 1/2 and 1/2. And suppose that I decide to repeat the same experiment successively many times with different particles and cats, but all having the same initial wave function. After many repetitions, for every possible sequence of outcomes, there will be some of my, quote, descendants, i.e. copies of me that exist in all the future worlds, that will see it. There will be a sequence of worlds in which the cats are always alive, and another sequence where they are always dead. There are also many sequences of worlds where the cats are alive 1/4 of the time and dead 3/4 of the time, and that is true for any other statistics different from 1/2. So that we can be certain that many of our descendants will not observe Born's rule in their world. Do I put the yeah. Let's see, wait, sorry, I'm going the wrong way. Let's see, wait a minute, is that? This one, do I go sideways? There we go. Okay, but one could argue on the basis of the law of large numbers that at least in the vast majority of worlds, the Born rule will be obeyed, since in the vast majority of worlds, the frequencies of dead and live cats will be close to 1/2 1/2. But what happens if instead of being 1/2 1/2, the probabilities predicted by quantum mechanics are, say, 3/4 1/4? We still have two worlds coming out of each experiment because these experiments have two possible outcomes. So the structure of the multiplication of worlds is exactly the same as when the predicted probabilities are 1/2 1/2. But now, if one applies the law of large numbers as above, one arrives at the conclusion that in the vast majority of worlds, the quantum predictions will not be observed, since our descendants will still see the cats alive in approximately 1/2 of the worlds, and the cats dead also in approximately 1/2 of the world, instead of the 3/4, 1/4 frequencies predicted by the Born rule. The second objection concerns the ontology of the theory. Some people argue that all there is the wave function, but that is just a mathematical object, a function defined on a high-dimensional space. It is then claimed that such a theory would be local. But since no connection is made with our three-dimensional world, I do not understand that claim. A connection with our three-dimensional world can be made if one introduces a continuous matter distribution, see the reference there, but upon examination, that theory turns out to be non-local, as it should be because of the EPR Bell result. Okay.
Are there any comments?
I'm going to stay here because I did the next one, yeah.
You are welcome to present.
Okay, should I go to the next one?
No.
Oh, I asked for comment. Yeah.
That one, maybe?
Yeah, you choose the color. You can see it.
I go.
No, sorry, I didn't see. Okay, so over there, I said it's not so good, so I.
So it's unsurprising but kind of amusing that it's very hard for people to answer the question, why is there no consensus, rather than the related question, why isn't it true? So, I mean, for reasons I've rehearsed so many times, obviously I think there are answers to the issue that Bricmont brings up. But if the question is, why isn't there a consensus? I don't think this is why there isn't a consensus, because my experience is, at least within physics, surprisingly few people care about the probability problem in the many worlds theory. And my anecdotal evidence for this is that some years ago when I was working on the decision theory material, I used to give a lot of talks to physics audiences about the probability problem. And I had to work really hard to get them to take it seriously. And eventually I got quite good at having a little summary, a little kind of capsule philosophy of probability to motivate to physics audiences why there was a problem with probability in the many worlds theory, so that I could then go on to tell physics audiences why, after all, there wasn't a problem in the problem. After a while, it dawned on me that I could do this rather more quickly.
Okay.
This is not particularly about Jean's comment, which obviously brings up issues that we've discussed in some detail. It's just to directly address the question that Lev asked, why is there no consensus for the many worlds interpretation? I just want to make two comments. One is, one thing we sure know now better, I know now better even than at the beginning of this conference, is there is no such thing as the many worlds interpretation. There are many different approaches that you could put under the broad umbrella of many worlds, which I think are held together by denial of the single outcome assumption, which gives you objective statistics that are independent of anybody's viewpoint or standpoint or branch or whatever. They're just statistics out in the world. But there's not a single thing. So there would be no, since there is no, you could say, why is there no consensus about a many worlds interpretation, even if there was, sectarian violence between the different branches. And the other comment I want to make is, I think all of this talk about, I talk to physicists, if the question is, why is there no consensus among them, we all know they have been systematically trained not to even consider foundational questions like this. Systematically, not just left on their own, systematically discouraged from asking the kinds of precise, exact questions about what the theory asserts, what the theory is committed to, which ought to be the center of our discussion. So if you ask me, why is there no consensus among them, I don't care. Why should I care? Why should I could go out and ask people on the street what they think. Okay, there's a statistical fact about that, but I don't care.
I don't think that you are right about physicists. What essentially, what I know, I'm really a physics professor, and what I know that among physicists who teach in quantum mechanics, maybe half of them will start that I will teach you how to use it. I don't know what it is. And it doesn't happen in any other area of physics. So there is a physicist who want consensus. They want to understand what are foundations of quantum mechanics. There are several papers, more famous or less papers, that this is the biggest scandal of physics. There is no consensus of foundations of quantum mechanics. And then the fact that maybe there are several many world interpretations, then why there is no consensus on the set of many words. The main thing, there is no consensus about foundations of quantum mechanics. I believe, I feel that, at least my particular version, how I understand, has no action to distance, and this should kind of win against everyone. Maybe others consider that's not so important.
I mean, partially I'm not disagreeing with you, Lev, in the sense that, as you say, many people will teach it, not address it. I mean, books don't address this, they don't address it clearly. I mean, we know, as a matter of fact, from the most recent Nobel Prize, which was very nicely given foundations, that the Nobel Prize Committee didn't understand what had been proven because they thought it disproved hidden variables. And they say that. Why should I care what they think?
so. I think so.
And
They didn't get it by a miracle.
nobody says they did.
Please don't hold the wireless mic too close to your mouth, so it will be heard better.
Oh, I did earlier, but I think what I had to say has already been said.
Any more comments?
And just in addition to what Tim said, not only have they been consistently taught not to care about foundations, but they have also been selected, because those that really wanted to understand what they were taught dropped out.
Was that the 3 years in which the photons weren't discovered and they all just felt in the dark and so they left?
Just a comment about probability. So I think I first, or most recently, I met Lev 12 years ago in a conference about probability honoring Itamar Pitovsky in Jerusalem. And I think, for example, Pitovsky's approach was that probability reflects human uncertainty and not some physical term, but he was not an advocate of the many world interpretation. So the idea that maybe probability is not an objective matter was widely viewed in other branches of philosophy, and they're not necessarily related to this interpretation. And about foundation, we can get a very limited learning from the analogy with mathematics. In the early 20th century, there was a foundational crisis in mathematics, so people were very heated about it, and then it was settled in a negative way, that there is no solution to the foundation questions in some sense, and it didn't have any effect it didn't have much effect on mathematics itself, both the crisis and the negative resolution, and the practice of mathematics remained very similar. So I can understand the rationale for not trying to worry too much about foundation, although I can also understand the rationale of trying to figure out the foundation.
I'm not sure we have enough time for another comment. It's has a very different character. So maybe somebody wants still to make some comment. If I'll make my question a little more narrow. We in the foundational conferences there are maybe now almost no conferences on quantum logic, but still we have, and I think consistent history had some popularity maybe 10 years ago and not now. But many words, it still doesn't win against maybe Bohm and GRW. So, and these others have this action at a distance. And so I don't understand how people consider on equal footing, like Valia presented this, that we have all these versions and they kind of, we don't know, they're all good. And, but for me, they don't look on the same level.
So I think there are rather few people who think both that the many worlds theory solves the measurement problem satisfactorily, and yet that it should be rejected in favor of alternatives. I mean, there aren't no people who think that, but the great majority of people who don't agree with the Everett interpretation, I think, also think not just that it's less desirable than other alternatives, but it's unacceptable because it doesn't solve the probability problem, or it doesn't have a clear ontology or a clear connection to experience, or these kind of lines. So there aren't that many people who could get the position you're advancing off the ground. It's not that, say, Tim is going to say, yeah, sure, many worlds theory solves the measurement problem, but it's unattractive compared to other options. Tim or David Albert or someone is going to say, no, it doesn't solve the measurement problem at all. It has no satisfactory account of probability. It has no satisfactory account of ontology.
Okay.
So I think it's been mentioned several times that it's the interpretation and the possibility of using this to encourage reformulations is maybe these are two different things. So what some of the people are doing are looking at different complete theories that aim to discuss a large range of phenomena, maybe not as large as David would like, but a large range of phenomena. And then they're saying, okay, let's look at the interpretation of this one, the other one, and see what looks finest. But others might be saying, maybe these problems, these foundational problems, are hints for developing more reformulations of quantum mechanics. And that's, you know, I'm talking about retrocausation and other possible, I mean, not just Kramer's version, some new version that would perhaps not reify the wave function.
This is related to the next quote, but we'll not discuss it now. Last comment, and we'll have lunch, I think.
So following the panel in which David argued that the many-world interpretation is indeed a consensus, and I was, when I was preparing my slides, I had this slide from one of those polls, and so indeed many argue that you could have superposition of macroscopic object in principle, but then many also believed that around 50%, sometimes it's closer to 20, 30, it depends on the particular poll, but that there is irreducible probabilities, which is, I think this is the point where the many worlds interpretation is definitely not the consensus, irreducible randomness. And I think that the reason for that has very much to do with what Tim, as far as I understand, correctly argued, that the Nobel Committee did not understand the Bell inequalities, which is basically remnants of the old debates about quantum theory, in which it was argued by von Neumann and by Heisenberg that the indeterminism is irreducible, and it is still there in the physics education and very basic, and I think it's basically one maybe sociological, historical factor. It is still there and probably wrong.
Okay, we still have 1 minute, yeah.
I should perhaps defend them, but I won't. I have written to the professor who presented the prize, which is normally the one who has been driving within the committee. And he only answered that he's presently on vacation and will respond when he's back. Perhaps you thought he was on vacation when he wrote it. So that's it. He is anyhow written, as I promised you.
Oh, we still have, maybe come for the last, oh, you can go here.
Yeah, I just wanted to say something about whether it should be a race between different alternative points of view, or whether they can coexist. I'm going to advocate for the second. Of course, one might have a favorite point of view, and until this conference, I thought mine was Everettian point of view, but I'm not so sure now. But anyway, I want to make the point that Feynman was raising in an entirely different an entirely different aspect. Of course, he was not talking about interpretations of quantum mechanics, but it's useful to have different point of views on the same phenomena, and of course, different interpretations really focus on different aspects of quantum mechanics. So it's really, I think, at least in my professional experience, it's very useful to have in mind as much as possible of them, and then to use them in different situations, and that is very useful, I think.
Okay.
I think there is a difference between formulation and interpretation. I think formulation, path integral, two-state vector formalism, I don't know, put together, sorry. This is all legitimate and helpful. But what is the ontology if there are some moment particles moving, or there is a collapse of the wave function? This should be resolved. I believe so.
Yeah, so, sorry, this is really just a comment for those who view this on YouTube eventually. And hopefully if Jean is listening, hi Jean if you're there, but just to say, he's raised the branch counting problem, the old branch counting rule, and the ontology problem. Both my talks at this conference exactly were addressing those problems. So viewers, please look at those earlier talks to see a developed response to Jean Bricmont there. Okay, thanks.
I can say that I don't hope that everybody will have a consensus on my view, but I hope it's remembered because I think maybe 100 years from now, that framework might accept it. Of course, hopefully they'll have more theories to what these awareness operators are.
Okay, let's thank all people who make contributions.